Assalamualaikum Chem30. So this will sort of continue off of where we left off for the fourth block, because we always have a shortened amount of time. And we'll get into the enthalpy change in the calorimeter. And what I will do is, for both classes, I will add on to the assumptions that we make, and I'll solve actually two problems in this video that have to do with enthalpy change. So before leaving, we actually mentioned enthalpy change, and we talked about it. And what we said was that it's the total energy that a system has. Now, the system only has potential energy. So what you're really doing when you're measuring the change in enthalpy is you're calculating how much potential energy the system gains or loses as a chemical reaction happens. Okay, so yeah, it's the change in energy, and it's more or less the change in potential energy. Now remember, this can't be measured directly. And why can't you measure the enthalpy change directly? Because you can't measure potential energy. We don't have a device that allows us to measure potential energy. We can measure heat and kinetic energy, but we can't measure potential energy, at least not chemical potential energy anyway. So enthalpy change is something that cannot be measured directly. So what we end up doing is we use what is called a calorimeter. And we use the conservation of energy along with the calorimeter. And we're going to say that this calorimeter here is dependent on the conservation, so we'll just write conserve of energy principle. And the conservation of energy principle is what? It's whatever energy we start with is going to be the same amount of energy that we end with. And so because we cannot measure enthalpy change directly, we're going to use something called a calorimeter to help us measure the potential energy loss or gain as it went through a chemical reaction. Now, a calorimeter could be anything. It's a word that could describe a whole bunch of things that look different, but their function is generally the same. When we say calorimeter, we're just talking about any device that'll change in temperature. So here it says heats up or cools down from a reaction that takes place. Okay, so if it heats up, we know that it's going to be an exothermic reaction. And of course, if it cools down, that's because it's an endothermic reaction that it is dealing with. And so this temperature change is used to infer heat transfer. And what we mean by inferring is that we're going to rely on the principle of conservation of energy to allow us to get the enthalpy change of the system. And so it says, and heat transfer is used to infer enthalpy change. The calorimeter is always considered to be the surroundings, and it should be an isolated system. However, we settle for a closed system. Okay, so it has a lid. We don't want any gases or heat escaping as much as we can. We don't mind heat entering the calorimeter, but we don't want it to escape. Okay? So again, the calorimeter is going to heat up as a result of a reaction that's often happening below it. In some cases, it's happening in it, and we'll see, exactly how that works. But a calorimeter will then take the heat. And here's the general understanding that we use. We said the principle of conservation of energy is what we use to determine the enthalpy change. Well, we know that whatever the change in potential energy is going to equal to the change in heat. So at this, I want you guys to write down in your notes the calorimeter equation. So the calorimeter equation is going to be the enthalpy change of the system, because remember, the system can't actually heat up. But as conservation of energy would have it, whatever change in potential energy, which is your enthalpy change, that the system experiences is going to equal to the heat, either lost or gained, by the surroundings. Now, when we say surroundings, what we really mean here is the calorimeter. So when I rewrite the equation, it's going to look like this, where it's the enthalpy change of the system is equal to the heat loss or gained by the surroundings, or negative Q. And we call this the calorimeter equation. Okay, or formula. So I want you to take a couple minutes and get that into your notes. And so this is how your typical calorimeter, at least not a very expensive one, would actually work. You'd have a fuel, it could be ethanol, it probably is. Let's say they're doing a combustion reaction. So this whole thing here is combustion reaction. Now remember, a reaction is a system. Now that system doesn't actually heat up or cool down. Remember, if I'm lighting a candle and I want to know how hot that flame gets, I don't actually stick the thermometer inside the fire. No one does that. And I don't recommend anybody doing that either. What's going to happen is as follows. You're going to have heat from the fire that gets directly transferred into the water. So we're going to write heat transferred to H2O in the calorimeter. Okay? And so my combustion reaction happens, it changes in potential energy, and whatever amount it gains or loses, depending if it's exothermic or endothermic, it's going to change that potential energy into kinetic energy or heat, and that's going to either get absorbed, right, or get removed from the water itself. So as a result, the heat transfers into the water, the thermometer records a change in temperature of H2O. Now, here's the key thing here. If we have a change in temperature of H2O, that makes H2O, or the water here, the surroundings. So I want you to take a minute and look what's happening here. You got the system, the combustion, right, of your ethanol or whatever is being burnt, that is changing in potential energy. And it's sending heat into the water, which acts like the surroundings because it'll heat up. The combustion reaction is the system. The water, because it heats up, is the surroundings. And so what we can do is use the temperature change of the water to get the heat of the water. And then from the heat of the water, we can infer the enthalpy change from the combustion of ethanol. And so our equation would look something like this. So we would have the enthalpy change of the combustion, right, of fuel, we'll just say whatever this is, it could be anything, of fuel is equal to the negative Q that is experienced of the water. And I know that there's a copper can here and everything, but we'll talk about some assumptions that we make, shortly. But whatever energy change this is experiencing is going to be told by the change in temperature of the water, because energy has to be conserved. Whatever energy change this is experiencing, the potential energy, is going to be the same heat that the water experiences. These two are going to equal each other. And so this is how this equation works. And so let's say I put some real numbers to this. Let's say that I have 100 milliliters of water and the temperature changed, right, as a result of the combustion of the water from 20 degrees originally to, let's say, it heated up. So let's say it's 27 degrees Celsius. Now, right off the bat, we know that this is an exothermic reaction because if water is the surroundings, we can see that the surroundings have heated up. So we got 100 milliliters of water and we have the temperature change. This would be our Ti and this is our Tf. And it goes from 20 degrees to 27 degrees. And so the question would be, and I'll write it here in black. And so a question could be, what's the enthalpy change or combustion, or the enthalpy change of combustion of fuel? So we're going to use our calorimeter equation where the delta H is equal to negative Q, which means that the delta H is equal to negative MC delta T. And of course, all these values are going to belong to the water, which we've mentioned over here. And so when we plug in our values, and we go delta H is equal to negative 100 multiplied by 4.19 multiplied by 20, it'll be 27, it's final minus initial, 27 minus 20 degrees. We end up getting the following value. And I'm going to write my answer over here because I'm running out of room. The enthalpy change is going to equal to negative 2,933 joules. Now, it should be in kilojoules. So what we're going to do is divide this by 1,000. And our final answer is delta H is equal to negative 2.933 kilojoules. I didn't specify on digits, but this is the final answer. And I want you to hone in on something here, kind of like what we were talking about. That negative tells us what? That it's exothermic. And we know it's exothermic, right? Because we could see some fire over here. Okay? So this formula, the temperature change, they all say the same thing in different ways. The enthalpy change tells us if the reaction is negative by showing us a negative, show us that the reaction is exothermic by showing us a negative value. And temperature shows us if a reaction is exothermic by showing that it increases. So this drawing up here is what we call the ideal calorimeter. And it should be an isolated system, which means that there's no matter or energy that's exchanged. But as we can see here, it's that's not really attainable, so we settle for a closed system. We also, and this is a big thing, and I want both groups to kind of, both classes to underline this part. We assume, now it's not really true, but we assume that no heat is absorbed by the metal calorimeter itself, and that all the heat is only absorbed by the water, which is why we say, that your enthalpy change is equal to Q of the water. If we were being really accurate, we would actually say of water plus the metal, because the metal, it does absorb heat, but we ignore that it does. And like some things in science, these assumptions are what happen to make they make our experiments simple, but they also make our experiments flawed. And so when we say enthalpy change is equal to negative Q of the calorimeter, what we really mean is that the change in enthalpy is equal to the change or the energy absorbed by water. And by energy, of course, we're talking about heat. And so to close off, we'll list some other calorimeter exceptions that we make. And one of them, the first and foremost, is that the can or cup itself does not absorb heat. We know it does, but for simplicity, we're going to try and pretend that it doesn't. And the other one is that all solutions, okay, have the same density as H2O. And so what that means is if I give you, let's say, a solution of sodium hydroxide or a solution of HCl, you assume that that solution is mostly water, and so we're going to treat it like water. So if I say 200 milliliters of HCl, you're going to pretend that it's 200 milliliters of water and put it in as you would for the mass and treat it like the surroundings. And so what we mean more or less is that let's say I had 200 milliliters of HCl, and let's say I even gave a concentration. We say of, this where solution is going to come into place, of 0.5 moles per liter, okay, HCl. This and this is treated like H2O. Okay, it's treated like H2O in the sense that 1 gram is equal to 1 milliliter, and that it's the surroundings. And I'll just put surroundings, just like that. So any type of solution is going to be treated like water, and it's going to end up being the surroundings. We'll get into more details like this on Monday. Inshallah, I hope this video helps. Assalamu alaikum.